Welcome to this explainer. We tend to think of artificial intelligence as this weightless, invisible magic, right? Something that just lives up in the cloud. Entirely digital, entirely effortless. But today, we are going to completely shatter that illusion. Because the truth is, there's absolutely no artificial intelligence without real, physical energy. The whole foundation of this digital revolution we're living through, it's built on land, minerals, massive industrial facilities, and quite frankly, a staggering amount of electricity.
And because of this massive physical footprint, as AI just rapidly expands across the entire global economy, we have to ask a very serious question. Can AI trigger the next energy crisis? Are we actually heading toward a future where our digital demands outpace our physical capacity to keep the lights on? Well, that is the exact question we're going to unpack today, and trust me, the stakes literally could not be higher.
Okay, let's dive into this. Our everyday experience with AI feels entirely effortless, doesn't it? Generating an incredibly detailed image or having it diagnose complex medical patterns in mere seconds. But right behind that effortless digital action is a highly intense physical reality. We're talking thousands of highly specialized computer chips operating inside enormous semiconductor factories, relying on miles of transmission lines, massive transformers, and a continuous, completely unbroken supply of electricity. An AI model doesn't just pull answers out of thin air. It computes them inside massive buildings that can consume as much power as an entire city.
How AI consumes power: building and running the engine.
So, AI essentially uses electricity in two very distinct stages. The first is training. Think of this as basically building the engine. To create an AI model, developers have to feed it massive, and I mean massive, volumes of text, images, or audio. The model processes this data over and over again to learn statistical relationships. Training just one major model can require thousands of advanced processors running at full tilt, continuously, for weeks or even months. It is incredibly energy intensive. But the second stage, which is called inference, is where things get really wild. Inference is running the engine. It happens every single time someone, anywhere in the world, asks a chatbot a question or generates an image. Now, while one single request uses just a tiny bit of electricity, billions of these recurring requests happening 24/7 all over the globe create a massive, continuous power load. And as AI gets cheaper and faster, well, people use it even more, driving that total electricity consumption even higher.
Now, what's really interesting about this slide is how that power is actually spent once it reaches the data center. A data center is essentially an industrial-scale machine. The servers themselves, the parts actually doing the computing, take up about 60% of the electricity. Storage and networking take about 5% each. But the really fascinating part is that remaining 30% slice. You see, heavy computation produces heat, and a powerful AI chip turns almost all its electricity into heat instantly. If that heat isn't removed, the equipment literally melts. It fails entirely. So in many data centers, nearly a third of all the electricity is used just to power massive fans, pumps, and chillers to stop the whole system from overheating. Think about that. When you ask an AI a question, a huge chunk of the power used is just to keep the computer cool enough to actually give you the answer. To really grasp the insane scale of this, just consider this single number: 65. By the year 2027, just one advanced AI server rack, which is a piece of equipment that takes up roughly the same physical space as your kitchen refrigerator, could demand the exact same peak power as 65 entire households. Seriously, picture your kitchen fridge for a second. Now imagine taking the electricity demand of 65 homes and compressing all of it into that exact same amount of space. Now imagine thousands of those racks operating together in a single giant warehouse. That is the true physical scale of the AI revolution we're talking about here.
Let's move to the global infrastructure divide and see how this builds. Specifically, where all this power is actually concentrated.
In 2024, data centers used about 1.5% of all global electricity. But here's the catch: that consumption is not spread out evenly at all. The United States accounts for a massive 45% of that total. China takes up 25%, and Europe represents another 15%. Do the math, and that means roughly 85% of all global data center electricity is concentrated in just 3 regions. Why? Well, because they already have the massive tech hubs, the advanced semiconductor supply chains, deep capital markets, and, most importantly, the massive existing electricity grids required to support these giant industrial facilities.
Now, this intense concentration creates a pretty stark and troubling economic reality. Developing and emerging economies outside of China contain more than 2/3 of the entire human population, and yet they possess less than 10% of worldwide data center capacity. The danger here isn't just about missing out on a cool new tech trend. No, it's a dangerous new development trap. These countries desperately need AI to boost their own productivity, but they lack the stable power grids and the massive capital to actually build the infrastructure. So what happens? They might end up just purchasing AI services from abroad, basically importing the tech while the massive economic gains stay in countries that already have strong grids. The digital divide and the energy divide are kind of starting to reinforce one another.
Section 3. Risks to the power grid. Digital speed versus infrastructure speed.
At the core of all of this is a massive mismatch in speed, and this brilliantly illustrates the problem. Global data center electricity consumption was hovering around 485 terawatt-hours in 2025. But by 2030, the International Energy Agency projects it could reach roughly 950 terawatt-hours. It's essentially doubling in just 5 years. Now, looking at the big picture, this is still only about 3% of total global electricity demand. But remember, electricity systems are inherently local. You can plan and build a massive new data center in 2 or maybe 3 years, but building the new power transmission lines required to actually fuel it, that takes much, much longer. You have environmental reviews, land acquisition, and tight supply chain constraints for things like transformers. Technology companies are moving at lightning-fast digital speed, but the power grid? It moves at a slow, plodding infrastructure speed.
And when those speeds diverge, we see 4 major localized risks emerge. First up, higher electricity prices. If power supply can't keep up with the data centers, costs go up. IMF modeling even suggests this could raise electricity prices for ordinary households if infrastructure gets too restricted. Second, competition for grid capacity. A massive new data center might end up directly competing with new housing projects or public transport for limited connection space on the local grid. Third, a renewed dependence on fossil fuels. AI needs power 24/7. Wind and solar are amazing, but they're intermittent. So if clean energy and massive batteries can't be built fast enough, energy companies might just extend the life of coal plants or lean heavily on natural gas just to keep those servers running. And finally, pressure on industrial competitiveness. If AI absorbs all the local power capacity, traditional industries like steel, manufacturing, or chemical production might face delayed grid connections or absolutely crushing energy costs.
Averting the energy crisis. AI as part of the solution.
But wait, before we jump to the conclusion that AI is just going to completely break the grid, consider this fascinating twist of irony. AI is actually an incredibly powerful tool for fixing the very grid it stresses. AI can drastically improve forecasts for solar and wind generation, matching them perfectly with user demand. It can analyze grid data to identify failing transformers long before they actually break down, potentially preventing blackouts entirely. It can even optimize heating and cooling in massive industrial systems. In fact, documented AI applications could produce incredibly substantial energy savings across the entire economy by 2035. So what we're really looking at is a race between two forces: the massive growth in computational power on one side and the incredible efficiency improvements driven by AI on the other.
So how do we make sure the efficiency side wins? Well, governments and planners have 6 actionable policies they need to implement. First, improve disclosure. Tech companies absolutely must be transparent about their future energy and water needs so grid operators can actually plan. Second, integrate energy and digital policy. You simply can't write a national AI strategy without a matching electricity strategy. Third, allocate costs fairly. Everyday households shouldn't be subsidizing the grid upgrades needed by private tech giants. Fourth, locate facilities intelligently. We need to build data centers in regions with spare power and cooler climates, not right next to already congested cities. Fifth, make computing flexible. Run non-urgent AI training tasks at night when electricity is abundant and cheap. And sixth, expand clean supply. Invest heavily in transmission, renewables, and battery storage. The goal is simple. AI expansion must add real value to the electricity system, not just drain what is already there.
So the crucial point is really captured in this one analysis that states, the future of artificial intelligence will not be determined by algorithms alone. It will also be determined by the grids that keep them alive. Look, a sudden worldwide blackout caused by AI? That's highly unlikely. The real limits of the AI revolution are purely physical and highly localized. A congested grid, a delayed transformer shipment, a sudden unexpected spike in a small town's electricity bill. Those are the gritty physical realities that will govern exactly how quickly our digital future can actually be built. And that leaves us with a final, pretty provocative thought to consider. The big question is no longer whether we have the algorithms or the data. We've got those. The real question is, Can we build the physical energy systems fast enough to support AI's explosive growth, fairly enough so that ordinary people don't end up footing the bill, and intelligently enough so that we don't accidentally plunge ourselves right back into a heavy reliance on fossil fuels? The digital revolution is absolutely here, but its ultimate success will rely entirely on our physical world. Thank you so much for joining me on this explainer, and I really hope this gives you a completely new perspective on the true physical cost behind that simple little search bar.